When we talk about the exchange of oxygen and carbon dioxide, especially as we talk about in reference to Dalton's law and oxygen and carbon dioxide exerting their own partial pressures in the atmosphere and therefore being able to move down their concentration gradient regardless of the direction of the other gas, we're going to look at Henry's law. Henry's law states that the quantity of a gas that will dissolve in a liquid is proportional to the partial pressure of the gas and to its solubility. This means that more gas will dissolve in a liquid if it's at a higher partial pressure and if that particular gas is soluble in that liquid. This also is related to temperature. Temperature changes will change the solubility of a gas. But in general, high partial pressures and high solubility mean as a gas is more likely to stay dissolved. So if we look back at the partial pressures of gases, we notice that carbon dioxide is generally 20.9% of atmospheric air and CO2 is 0.04% of atmospheric air. So we have a large number of oxygen molecules in atmospheric air compared to CO2. But we have more CO2 dissolved in blood plasma than we do oxygen. Most oxygen has to be bound to hemoglobin to be carried through the bloodstream because its solubility in blood plasma is very low. The solubility of CO2 is 24 times that of oxygen, so we have more CO2 dissolved in plasma than we have oxygen. So these things all depend on how soluble a gas will be and how it can remain dissolved in a liquid. So that means if a high partial pressure and high solubility are there, more of that gas will remain dissolved in liquid. This means that if we can increase the partial pressure of gas, we can make it dissolve in a liquid more often. So here we see under normal conditions, the little particles, the red particles, are going to be the gas, and we see it in a liquid there. Notice that when we increase the pressure on the right side of the figure, the gas molecules will be forced to dissolve in the pressure more, be dissolved in the liquid more because we've increased the partial pressure. This is what happens in a carbonated beverage. So what happens in a carbonated beverage is that beverage is capped, and it's done this under pressure where we increase partial pressure of CO2 and force it into solution. Whenever we open the soda, we have this hissing sound because that CO2 is escaping from where it is in a very high partial pressure to a lower pressure really quickly because there's such a big pressure gradient there. And whenever it does this really, really quickly, it's going to generate bubbles because it's coming out from that high to low pressure really fast. And of course, shaking it up can agitate that even more. So a carbonated beverage just means that we forced more gas to stay dissolved in the liquid because we've increased its partial pressure, thus making it more soluble in the liquid. So we can relate this to increasing partial pressures in the body. And the easiest way to talk about this is if we talk about scuba diving. In scuba diving, one of the things we're going to look at is the effects of nitrogen. So going back, we saw on a prior slide that the majority of atmospheric air is made of nitrogen. It is 78.6% of atmospheric air. But in general, we don't hear a lot about nitrogen, and that reason is because it doesn't stay dissolved in plasma very much. It's not very soluble. Now, obviously, this will change if we're scuba diving and we are breathing compressed air and we are at a below sea level, we are increasing the partial pressure of nitrogen, which means that we can force it to dissolve in blood, force it to dissolve in liquid. So there are changes physiologically if we force more of that nitrogen to dissolve in blood. So it has no known effect on body functions, but if you are scuba diving at a deep level and you force more nitrogen into your blood plasma and you do this, you stay down too long, too much bottom time where you have too much nitrogen, it can cause something called nitrogen narcosis. And here we see in the top figure, this is a quote by Jacques Cousteau. The chief symptom of nitrogen narcosis is, to put it bluntly, the sensation of becoming as drunk as a hoot owl. It gives an intoxicated feeling, which on the surface may not, if you're in a safe area, be as bad. But if you are under the water at 70 feet and you're trying to take your regulator out of your mouth and give it to a fish, then it's not going to work very well for you. The other thing we can think about when dissolving nitrogen in plasma when we're scuba diving is the same effect as with the soda. So if we have forced nitrogen into the solution under a partial pressure, one of the things you'll learn in scuba diving is you can't just be diving at a deep level and then swim really quickly to the surface, because that gas will expand when it's coming up to the surface. Also, it's going to be like the figure of the soda you see here on the right. Whenever we go from something in a high partial pressure toward a lower partial pressure, that nitrogen is going to work its way out of the blood really quickly. And it's going to be like this soda where it's going to create nitrogen bubbles. And there we see the effects on the bottom figure where she has the busted blood vessels, and you also see the arrow pointing to the joint there where there are gas bubbles in the joints, which can be painful. This is called decompression sickness, but it can also be called the BENS, B-E-N-D-S, just because it can make pain in the joints as gas bubbles get there, like you see in this image. And maybe some of the worst effects is if you get an air embolism that lodges somewhere like a pulmonary capillary as those bubbles come out. So decompression sickness can be dangerous as well. If someone experienced decompression sickness, they would end up having to go into a hyperbaric chamber, which some hospitals have. And what that does is put you into a chamber that increases the partial pressure of those gases again. So they just put you back under pressure and then slowly let that pressure off. So that's what would end up happening in that situation.